Lecture 31, Experimental Rock Deformation. So far, we have treated stress and strain separately. But now we must ask the question of how materials deform in response to stress. The study of the mechanical properties of solids, fluids, and gases is known as rheology, from the Greek rheo, which means to flow. Experimental rock deformation refers to the laboratory study of the mechanical properties of rocks. These include the response of rock to stress, or rheology, the maximum stress that can be sustained by a rock, or strength, and the resistance to sliding on a fracture surface in the rock, or friction. This figure shows the most common types of rock tests in the laboratory. In most tests, we use a decimeter-size cylinder, 2 or 3 times as long as its diameter. We can apply to the cylinder the same all-around stress. This test is known as hydrostatic. We can apply just a stress along the long axis. This test is known as uniaxial. We can confine the sample under a stress, and then apply compression or tension along the long axis. These tests are known as triaxial and triaxial extension, respectively. Finally, on a rock cube, we can apply different stresses to the faces of the cube. This test is called polyaxial or true triaxial. The uniaxial and triaxial tests are the most common. The polyaxial test, because of its complexity, is rare. Here is a picture of the triaxial test. The cylindrical rock specimen is placed inside a vessel and is subjected to a confining pressure P(C). An additional valve controls the pore pressure, Pp, within the specimen. Then an axial platen is used to load the specimen. During the test, one can measure the axial and radial strain of the sample, the pore fluid pressure, and the axial stress. The results of this test are plotted in a stress versus strain graph. The x-axis is the axial strain, and the y-axis is the differential stress, sigma 1 minus sigma 3. The stress-strain curve is first nonlinear because of cracks closing in the sample. Then, the behavior is linear or elastic, followed by nonlinear or inelastic, and finally rock failure, which is marked by a drop in the stress. From the stress-strain curve, one can measure the following elements: the slope of the linear, elastic part, the differential stress at the onset of inelastic behavior, which is known as the yield strength, the maximum differential stress, which is known as the ultimate strength or just strength, and the differential stress and strain at failure. This figure shows representative stress-strain curves. A is elastic deformation followed by brittle failure. B is elastic deformation followed by yielding and failure. C is elastic deformation followed by yielding, strain softening, and failure. Strain softening means less stress is required to strain the sample. Stress hardening is the opposite. D shows strain hardening followed by strain softening. E is elastic deformation followed by yielding and plastic deformation, where the sample deforms at the same level of stress. And F is elastic deformation followed by yielding and strain hardening. Let's look at the elastic regime, or linear part of the stress-strain curve. The slope of the curve in the elastic regime is a measure of the stiffness of the rock. Elastic deformation is instantaneous and recoverable deformation. When the rock is stressed, it instantaneously becomes strained. When the stress is removed, the strain disappears immediately. This figure shows 3 types of loading of a rock cube and the parameters in the elastic regime. Blue is the initial geometry, and red is the final geometry. For uniaxial stress, the ratio of the axial stress and the axial strain is the Young's modulus, E. The negative of the ratio of the lateral strain and the axial strain is the Poisson's ratio, nu. For simple shear, the ratio of the shear stress and the shear strain is the shear modulus, G. And for triaxial stress, the ratio of the mean stress and the volumetric strain is the compressibility, K. The figure to the left illustrates the Poisson's ratio for a rubber band under an axial load. The Poisson's ratio is the negative ratio of the lateral strain and the axial strain in the band, which are estimated from an undeformed circle and its deformed ellipse in the band. The figure to the right shows a nice application of the Poisson's ratio, a bottle stopper. The possible values of the Poisson's ratio are between 0 and 0.5. Rubber has a Poisson's ratio of about 0.5. It is nearly incompressible and maintains a constant volume by laterally expanding just enough to compensate for a given shortening. Cork has a Poisson's ratio of about 0. It is perfectly compressible and can be shortened without much laterally expanding. Therefore, a cork stopper can be cylindrical, while a rubber stopper must be tapered. This table lists the values of the Young's modulus and Poisson's ratio for different type of rocks. Notice that the Young's modulus is in the order of gigapascals, and the Poisson's ratio can be as low as 0.08 and as high as 0.40. In average, rocks have a Poisson's ratio of about 0.25. Let's look now at the inelastic part and failure of the stress-strain curve. This table shows the uniaxial tensile and compressive strength of different type of rocks. Rocks are weaker in tension than in compression, about 1 to 2 orders of magnitude. The compressive and tensile strengths are in the order of megapascals. The strength and ductility of rocks increase with confining pressure. Ductility is a measure of the amount of inelastic strain before rupture of the sample. These are stress-strain curves for two rocks under a range of confining pressures, from 0 to 200 megapascals. The stress-strain curves are shown in the lower row, and the strength and ductility versus confining pressure curves are shown in the upper row. We can see that both strength and ductility increase with confining pressure. This is another example for marble and limestone. In the marble, the strength increases with confining pressure, and the sample exhibits more strain hardening at higher confining pressures. In the limestone, both strength and ductility increase with confining pressure. At low confining pressures, the limestone behaves brittly, and at confining pressures higher than about 100 megapascals, the limestone is ductile. These are examples of brittle failure in triaxial test specimens of basalt. From left to right, the confining pressure increases from 0.1 to 98 megapascals. Notice how at a confining pressure 0.1 megapascals, the sample fails along an axial, tensile fracture. At 49 megapascals, the sample fails along an inclined shear fracture. And at 98 megapascals, the sample develops an array of inclined shear bands, and the deformation is much more distributed. The deformation in A and B is brittle, and in C is more ductile. Rock strength is also affected by temperature and strain rate. Here are two examples. In general, rock strength decreases with increasing temperatures, and rock strength increases with increasing strain rates. It takes less stress to deform a rock slowly than rapidly. Rock strength is also affected by fluid pore pressure, pp. The left graph shows this effect on a sandstone. At room temperature and at 300 degrees centigrade, the strength of the sample decreases with increasing pore pressure. As shown by the graph to the right, this is because as the internal fluid pore pressure in the sample increases, the effective confining pressure decreases. Rock strength is controlled by effective stress, not by total stress. For rock deformation, time is very important. The results of a constant strain rate experiment can be plotted not only on a stress-strain plot such as figure A, but they can also be plotted on a strain-time plot such as figure B, which shows how strain changes as function of time. The plot for a constant strain rate experiment must be a straight line. In creep experiments, the differential stress is held constant over time. Such tests can be depicted by curves on a stress-strain plot such as figure C, but the curves do not say how strain changes as function of time. Therefore, it is much better to plot the results on a strain-time plot such as figure D. The plot for a creep test is usually not a straight line, because the strain rate changes as strain hardening or strain softening occurs. A creep experiment on a strain time graph typically has 3 parts before rupture. The first one of decreasing strain rate is called primary creep, the second one of constant strain rate is called secondary or steady-state creep, and the third one of increasing strain rate is called tertiary creep. The flow of rocks through time is described as viscous deformation. Here, we need to look at stress as function of strain rate. If the relationship between stress and strain rate is linear, we call the rock material Newtonian. If it is not, the material is non-Newtonian. The slope of the stress-strain rate curve is the viscosity. A Newtonian material has constant viscosity. A non-Newtonian material has variable viscosity as function of strain rate. For these materials, the local slope in the stress-strain rate curve is called the effective viscosity. The viscosity of water is about 10 to the minus 3 Pascal seconds, that of basaltic lava is about 10 to the 3 Pascal seconds, that of glacial ice is about 10 to the 12 Pascal seconds, and that of Earth's asthenosphere is about 10 to the 20 Pascal seconds. Thus, the viscosities of Earth materials span at least 23 orders of magnitude. Rock salt is a very special material. Salt has lower density and strength than other rocks. This figure shows the differential stress required to fail salt as function of strain rate, and at room temperature. 2 fields are identified. In the light green field, salt fails brittly. In the dark green field, salt flows without fracturing. The line separating these 2 fields is the brittle ductile transition. In the brittle regime, the curves at increasing confining pressure show that the strength of salt increases with confining pressure. However, the higher the confining pressure and the lower the strain rate, the less likely is rock salt to break. At strain rates below 10 to the minus 10 per second, the brittle field disappears entirely. This means that at natural strain rates, rock salt cannot break, even at room temperature. Salt effective viscosity is dependent on grain size and temperature, and it ranges from 10 to the 17 Pascal seconds for small grain size and high temperature, to 10 to the 21 Pascal seconds for large grain size and low temperature. To learn more about this topic, please read Chapter 6 of Fossen, and do his e-learning module on rheology. And answer these questions.